What we want to talk about today is something called mole-to-mole conversions. This will be in your science lab book on a brand new right-hand page, and we're going to title this mole-to-mole conversions. Make sure that you put your page number up in the right-hand corner, and then we'll put today's date. Here's what we kind of think of when we think of mole-to-mole conversions. That might not make like a whole lot of sense, but really what it is it's just a ratio between any two things. It will allow us to convert any one thing into something entirely different. That might not make a whole lot of sense, but we got a pretty good example of what we mean by that. So what we want to talk about is making pizza. We want to talk about the different ingredients that are going to be involved. Ours is going to be pretty simple. We're going to have some crust. We're going to add some cans of tomato sauce. We need cheese, lots of cheese. So cups of cheese. This is going to be a pepperoni pizza. So we're going to put some pepperoni on there as well. And when you bake it, so here's baking it in the oven, we get we get ourselves some pepperoni pizza. So I left all these little blank arrows here in the front because this is actually really similar to how a chemical reaction goes. This simple kind of recipe for making a pizza can be made similar to a chemical formula. What we are going to do here though is we're going to fill in kind of what these are. So when you make a pizza, you only need, one crust. Based on the type of tomato sauce that we're getting here, we only need one can. I love cheese, so we're definitely going to put a lot on there. We're going to put 4 giant heaping cups of cheese on top, and let's say we need like 14 pepperoni on a pizza. When we put all those things together and put it into the oven, we only get 1 pepperoni pizza. So that's our quote unquote balanced chemical reaction for this pizza that we're going to be making. What we want to kind of figure out is, how much of these things we may need when we go to purchase it or kind of work with actually making this real pizza here. When I go to the grocery store, I need to buy myself some pepperoni because I'm going to make the pepperoni pizza. I'm thinking, I'm going to make a lot of pizzas. I'm going to have a giant party here, have lots of pizzas for everybody, and I also want not to spend a whole lot of money, so I'm going to try and buy relatively cheap or inexpensive pepperoni, and so I look for the biggest pack I have available to me, and there's in this pack of pepperoni here, it comes in packs of 112 pepperoni. So I want to make as many pizzas as I could with all the pepperoni I have. This is going to be kind of my dictating piece here because the crust is relatively inexpensive, so is tomato sauce and cheese, but the pepperoni is the meat portion, so I'm going to kind of use it to dictate how many pizzas I can make maximum, my theoretical maximum number of pizzas that I can make. Well, what I can do is I can actually set up a T-table here to help me figure out how many pizzas this would ultimately help me make. So in this case, I'm going to use our 112 pepperoni as my given, and we're still going to leave this kind of area here on our T-table blank, and I can create a relationship with this. So in this case here, what I'm going to use really is an ingredient to ingredient ratio. And the ratio that I'm looking at is my relationship of pepperoni to total number of pizzas I'm going to make for my party. So this is our ingredient number 1, ingredient number 2, so to speak. I mean, the pizza itself is our product, but this is our ingredient to ingredient ratio for our example of making pizzas. If I treat these guys as units, then I can copy pepperoni down here, and I can put pizzas up here. So I'm going to take the 14 that goes along with pepperoni, and 14 will go down with my pepperoni unit. And of course, for every 14 pepperoni that I consume, I'll be able to produce 1 pizza. So now we need to do 112 divided by 14, and that looks like it comes out to a solid number of 8. This will allow me to make 8 pizzas total. Okay, so now I can make 8 pizzas. That's kind of what we have determined. If I buy this pack of pepperoni, I can theoretically make 8 pizzas. What I want to do though is figuring out how much cheese I'll need to buy. So if we have 8 pizzas in total, let me flip to the next page here. So we determined that we're going to make 8 pizzas. I need to figure out how much cheese. So I'm actually going to do a little bit of backwards work here. So I'll set up a T-table. I'm going to go ahead and put my 8 pizzas up here. I'm going to put nothing underneath. And then what I need is a relationship between pizzas and cheese, because that's how much I need to buy. So remember from our balanced equation just on the other page here that we needed 4 cups of cheese in order to produce 1 pizza. When I go to fill in the rest of our t-table here, I'm going to use that information, our ingredient to ingredient ratio. And so I'll be putting my 1 pizza down below, because this unit up here always goes diagonally down. And then on top here, I'm going to put my 4 cups of cheese. So we have 8 times 4, we get 32 cups of cheese. Now, in this example here, we're talking about ingredients, but really what we can talk about is basically anything. We can talk about anything as long as we have a balanced chemical equation. So you guys have already learned how to balance a chemical equation, and we can use those balanced chemical equations to tell us how much of stuff we might need in order to do whatever reaction it is that we want. So in reality, we don't use these ingredients, but what we would do is something like this reaction here. So let's do our first example. We would take something like H2C2 and add that to oxygen. This H2C2 here is acetylene gas, so it's very combustible. A lot of people use it for welding and cutting metal. Just like most combustion reactions, we're going to end up producing CO2 and H2O. Now, in order to balance this guy, we have to do a couple of things and jump around here a bit. So what I see here on this side, on the right hand side of this equation, this number of oxygens is always going to be even no matter what number I put out in front of this. Its coefficient times the 2 down here will always make the total number of oxygens coming from CO2. Those will always be even. Over here I see the exact opposite. If I put a odd number here in front, I'm going to get an odd number of oxygens here because it has a 1 for its little subscript. What I know for sure is this left hand side, it only has 1 source of oxygen. So this source of oxygen is always going to be even, which is going to actually force this side here, tells me that this number, whatever it needs to be, also needs to be even. So the only candidates of numbers I can have out in front here are going to be even numbers. As I continue to kind of look at this, I'm going to try this out. Let's try with a 2 here at first, which would mean I would have 2 times 2, that's 4 hydrogens. I'm going to put a 2 on this side as well. That gives me 2 times 2, that's 4 hydrogens. But it also means I have 2 times 2 on my carbon, which is 4. So I'm going to try and put 4 here. So I have 4 carbons now. And that also actually gives me quite a few oxygens. So let's total up my oxygens on the right-hand side of the equation here. I have 4 times 2, that's 8 oxygens. And I have 2 times 1, that's 2. So in total I have 10 oxygens. The way I can get 10 is 5 times 2. So that's our balanced chemical equation here. Now that this is balanced, now we can get into the multimole ratios, or the multimole kind of conversions, which is the same as what we were just doing with all of our ingredients. What I can try to do here is something like this. If you had some quantity of the acetylene gas, so say that was 2.827 moles of H2C2, the question would be, how many moles of O2, which is just oxygen, are needed to react with all of that? So if I wanted to do this entire reaction here all the way through and react everything, all 2.827 moles of H2C2, how many moles of O2 would be needed? First, what we need to look at is a real mole-to-mole ratio. I need to compare moles of my acetylene here to moles of O2. So the number that we're going to kind of look at is this 2 here and this 5 here. This is going to help us establish our mole-to-mole ratio. So really what this equation as it is says is that 2 moles of H2C2 will react with 5 moles of oxygen to produce 4 moles of CO2 plus 2 moles of H2O. Well, we don't have exactly 2 moles of the acetylene. We have 2.827 moles, so I know that I won't have exactly 5 of oxygen, but it'll be somewhere maybe kind of close-ish, kind of in that neighborhood. It won't be a huge number, it'll be somewhere in there. But we can know exactly, we can actually do this perfectly. We can use this mole-to-mole ratio, the 2 to 5 ratio, to calculate this. So here, let's just go ahead and do that. Set up our t-table. Our given is 2.827 moles of H2C2, smiley face down below. Now, we have to be careful, and I would recommend that you guys start to kind of adopt this if you haven't already. We can keep track of our units, and we're pretty good about that. Everyone's been doing a great job on that front. But the thing that you're going to want to kind of add to your units now is the molecule or the substance that we're talking about. So I can't just say moles. I now have to say moles of H2C2 because here's what's going to get weird. I'm going to copy this unit down below like we always do, so it needs to go diagonally into this box. Moles of C2H2, and this is what I mean by it gets weird. We're going from moles of something to moles of something. So our new unit is actually going to be moles of oxygen. This is why we want to keep track of the substance, because otherwise everything has moles and it looks like everything would cancel or multiply and it would just get all kind of weird. But this one will only cancel with this one because we're talking about specific kinds of moles. Now, whenever you have moles over moles, you're going to always look at coefficients of those things. So here are your coefficients from a balanced chemical equation, and they are going to be what you need to use in front of these values down here. So moles of oxygen in this balanced equation, at least what we're talking about, it's going to be 5, and the moles of H2C2, acetylene gas, is going to be 2. So this mole to mole ratio, this 5 to 2, 5 moles of oxygen to 2 moles of acetylene gas, that comes from a balanced chemical equation, and that's always going to be kind of the case. Now, what you have to be careful about is once we start covering mole to mole conversions, we end up getting into kind of a sticky situation where we forget what we have already learned about molar mass. Just kind of as an aside here, I'll kind of just hop up here. When you're talking about molar mass, don't forget that it's the number off the periodic table of grams, and that's per 1 mole. That's always going to be true. It's going to be whatever substance you're talking about. You're going to add up all those values from the periodic table, and it'll be based on 1 mole. The reason I'm pointing this out is as soon as we start to cover this mole to mole conversion, right here, once I start to point out this, we start to see all of these numbers pop up underneath here. Alright, let's quickly do this calculation. So what we're going to need to do is take 2.827, multiply by 5, and divide by 2. And our answer is 7.0675, and we got to double check our unit here is going to be moles of oxygen. Okay, we have 4 sig figs, 2, 8, 2, and 7. So my answer needs to have 4 significant figures as well. So I'm going to chop it off right here at the end. And because we do have a 5, that means I need to round up on my 7. So the answer that we can finally report is 7.068 moles of oxygen. Now, to quickly understand kind of what we just did here and what this means in actuality, it's actually kind of awesome and a powerful thing. This is where chemistry, I think, actually gets interesting. What we can do is we started with some amount here. We started with 2.827 moles of acetylene gas. Well, the balanced chemical reaction up here, that's really our recipe. Just like our situation with the pizzas, this is a recipe. It's saying you need 2 moles of this to go with 5 moles of this to make 4 to make 2. Okay, well, that's not always the case. Just like we did, I didn't make exactly 1 pizza. I didn't follow my pizza analogy perfectly, right? When we did our kind of ingredient setup and created this little way to make a very simple pizza, I'm not just making 1 pepperoni pizza because I wanted to make a ton of pizzas for a party and I wanted to save some money, so I bought a pack of 112 pepperoni. From there, I had to figure out, well, how much I needed for other stuff. The other things are kind of easy mentally. Once we figured out that we were making 8 pizzas, it was like, oh, well, duh, if you're making 8 pizzas, you need 8 crusts. Or if you're making 8 pizzas, you need 8 cans of tomato sauce. But it was a little bit more complicated for us to figure out how many cups of cheese it was, so that's why we did this calculation at the top of this page to get the 32. The same thing is true in chemistry. Chemistry is just like cooking, we just can't lick the spoon. We want to react and use up all of our acetylene gas as best as we can, but we need to use this balanced equation to figure out how much oxygen I would need to supply. In this case, it gives us an answer, 7.0675 moles of O2. And then once we applied our sig figs, we get 7.068 moles.